This is chapter 15. We're now going to talk about a completely different class of compounds. These are benzene and aromatic compounds in general. Benzene is the most famous example of an aromatic compound, so that'll be most of the problems that we're looking at, but we'll also look at general definitions of aromaticity. All right, so aromatic compounds, they're called that because a lot of them have distinct smells, but not all of them do. They were discovered in the late 1800s, and they were unusually stable. A lot of them had distinct smells, so they were called aromatics. They've got a unique reactivity. So these aromatic compounds are oddly stable. Resonance structures and symmetry creates this heightened stability. And these aromatic compounds are much more stable than conjugated dienes. So you're going to see that they're like super conjugated. That's not even really a word. But benzene is the most famous aromatic compound. It has a 1-to-1 ratio of carbons to hydrogens, C6H6. This is really rare. And the discovery of benzene was interesting. They knew that it existed for a while, but they couldn't figure out what the structure was. So they knew the formula, they knew the weight, but they couldn't figure out the exact structure. This is back in the late 1800s where there weren't a lot of characterization techniques. Like they didn't have the mass spec that we have now to look at fragmentation patterns, right? They didn't have NMR. So some of the people working on it were really stuck, and rumor has it that this guy fell asleep and had a dream about a snake eating its own tail. And he woke up and thought, oh, it's a ring. The structure's a ring. All of our data makes sense if this is a ring. And they say that's how the structure of benzene was solved. So if you're ever really stuck on something, just go take a nap, right? The subconscious can work through a lot of stuff. So when we talk about electronic stability and symmetry, I want you to look at an electron density map of benzene and cyclobutadiene. So benzene has 6-fold symmetry, meaning that you could draw 6 different planes of symmetry through this. And cyclobutadiene is not as symmetric. So I want you to think about evenly distributing weight across something, right? Something is more stable if you've evenly distributed the weight across the whole. Think of it as like a wobbly tabletop, right? If you evenly distribute all the weight across the tabletop, then it's going to be more stable than if you unevenly distribute that weight, right? The table is more likely to tip. And we're going to learn later that what has to be stabilized in benzene is an intermediate possible positive charge in the center, inside the ring. So if you've got even electron density inside the ring here, that's going to help to stabilize that. But more on that concept later. So here is benzene in terms of the Kekuli structures and the resonance images. So benzene is a 6-membered 6-carbon ring with alternating single, double, single, double, single, double bonds. So this is a conjugated cyclic ring. It's also got a specific number of pi electrons, which we'll talk about in a little bit. But if you look at resonance, you could have this bond move here, this bond move here, and this bond move here, and you would have the other resonance structure of benzene. So benzene is drawn like this, showing every atom. It's also drawn like this, showing the stick figures. And it's also drawn like this to show both resonance structures simultaneously existing. Because what we learned from resonance was these structures don't completely exist one at a time. You don't have this 50% of the time and then this 50% of the time. What you actually have is you've got an average of these two structures, where the electrons are completely delocalized around the ring, and that is what this cyclic structure, this circular structure shows. So you could see benzene represented in any of these ways, right? They all mean relatively the same thing. So aromatics have a lot of good uses. We've got aromatic compounds in some of our amino acids, right? Tryptophan, tyrosine, and phenylalanine have aromatic rings inside of them, but also a lot of organic aromatics are pretty dangerous. So benzene is not great, pyridine is not great, and as far back as 1775, a British physician found that there was a really high rate of cancer in chimney sweep boys, and they attributed it to their exposure to soot. Years later, we found out he was correct because this compound, benzopyrene, this is an aromatic compound that shows up in soot, in charcoal meats, cigarette smoke, all sorts of stuff. And this was actually the carcinogen that he correctly associated soot with the high levels of cancer in these boys. So definitely pros and cons to aromatics. They're also very powerful synthetic compounds that we can use to do a lot of different things in organic chemistry. So it's always something to treat with a lot of respect. When you're in an actual physical lab doing experiments and handling chemicals, it's very good to have a lot of respect for these, right? Gloves, goggles, work in the hood, all that stuff. But like I said, there are a lot of biologically active organic compounds that do good things, right? We've got phenylalanine, the amino acid. There's other amino acids. And then a lot of active drugs actually have aromatic bases to them. Aspirin has an aromatic ring in it, ibuprofen, and then amphetamine and adrenaline compounds that, amp you up. So a lot of these things have anti-fever activity, anti-inflammatory, stimulant. Some of them are in our neurotransmitters, all sorts of stuff. So they are very important biologically as well. When you go on to take biochemistry, you'll see quite a few aromatic rings show up. So let's talk about nomenclature of aromatics. We've got the common system versus the IUPAC system. And these aromatic compounds have been studied for so long that we see the common naming system pop up and kind of meld with the IUPAC system more than we do with some other compounds. So we're going to be seeing some common names pop up that are accepted in the IUPAC system. We'll go over both. So there are two different ways that you could name this. You could name this something like hydroxychlorobenzene, which would be following the IUPAC system, right? The IUPAC system would say that this is 2-hydroxychlorobenzene, but the common name for something with an OH is phenol, and it's actually accepted to call this chlorophenol. And you'll also notice that we say O-chlorophenol instead of 2-chlorophenol. So there's a variety of different things when we're learning how to name aromatic compounds. We're going to have to learn the base names, like this with an OH is called phenol, but if you put a methyl group on that, it's called toluene. So we'll have to learn the common base names, and then we're also going to have to learn what this O means. We can see O, M, or P on there. And those are signifiers for the positions that the substituents are on. So here are good benzene derivatives to know, right? These are the most common ones that are going to pop up. I don't really see the last three very often, but you are definitely going to see phenol a lot, toluene, benzoic acid, benzaldehyde, styrene, anisole, aniline. All of those are going to pop up quite a bit. So you'll see they all share an aromatic ring, and then it's just changing the identity of this one substituent that gives it a base name. So if it's a cyanide group, you call it benzonitrile. If it's a OH group, it's a phenol. So this is an aromatic alcohol. We're actually going to spend a little bit of time on reactions of phenols as well. You put a CH3 there, you call it toluene. You put a carboxylic acid on, you call it benzoic acid. If you put an aldehyde, then it's benzaldehyde. If you put a methyl ketone, then it's acetophenone. A double bond is styrene, and this is the monomer that forms polystyrene. If you have a methyl ether here, OCH3, it's going to be anisole. Put an amine there, it turns into aniline. And then an SO3 is benzene sulfonic acid. Two methyl groups directly next to each other is called orthoxylene or O-xylene. And then three alternating evenly spaced is called mesitylene. So let's look at working these common names that are accepted in the IUPAC field into actual names. Okay. So this is what I mean. We had phenol, and we call it O-chlorophenol. Now, O basically means next door. We'll go over that in a second. If you've got your reference position here at the OH, this is 1. And then if you go over to the second position, that is called ortho. Also, if you go 1 over this way, it's called ortho. So there are 2 ortho positions on here. So this is called orthochlorophenol, right? So we use this system. We either call it O, ortho, M, meta. Meta would be these 2 positions. And then para would be directly across from the OH. So we call it either O, M, or P if we've got 2 substitutes on a ring. But if we've got tri-substituted rings or more, we can't use the ortho, para, meta thing anymore. So we've got to name it like a classic IUPAC compound. So this one here with 4 different groups on it, it's got 3 different NO2 groups and 1 methyl group. We would actually call this 2-methyl-1,3,5-trinitrobenzene. So notice with 2 substituents, we use the ortho-para-meta system, but with 3 or more, we have to use our classic IUPAC system, right? Now, if we name aromatic rings as substituents, meaning they're not the biggest part of the molecule, then we call them a phenyl group. So notice here, this is not benzene with something hanging off of it. It's actually octane with a phenyl group hanging off of it, right? The longest chain is 8, and this is a phenyl side group, right? So if that ring is the main part of the molecule, you call it benzene or phenol or whatever derivative it is. But if it's smaller than the rest of the molecule, the longest chain, then you call it a phenyl group as a side group. So let's talk more about what makes aromatics so stable, right? We have this delocalization of electrons that occurs with resonance. So you've got both of these existing as an average of each other. And all of these electrons, instead of thinking of it as 3 double bonds and 3 single bonds, think of it as every bond has 1.5. Every part has 1.5 bonds, right? And this delocalization actually happens in a really weird way. We're looking at this benzene molecule coming out of the plane of the page. So this is perpendicular to the screen that we're looking at, and it's coming out toward you. So there are pi orbitals, p orbitals that are actually sticking up and down out of the plane. And it's all these orbitals that talk to each other and pass these electrons around in these donut shapes. So the delocalization of p orbital carbons is what gives this an insane stability. All right, so this shows that we've got a planar molecule, and the 6 carbon atoms are at every hexagon point. They have the delocalized electrons above and below the plane of the ring. And it's resisting addition reactions because those reactions would actually bust up this delocalization. So they don't want to come in and break any of these double bonds because they don't want to break up this uninterrupted delocalization, right? Here's another way to view it. Here are the p orbitals that I was talking about that go above and below the plane, and it's those that actually share the electrons, right? So if you look down on the top, it just looks like a big blob. If you look at it from the side, you see 2 regions of electron density where they're all delocalized and shared equally throughout the molecule. Now, I've pulled from a few different websites for this presentation because you don't want to deal with my artistic renderings. I highly recommend the links that I've put here. Check them out because there are a lot of other good images and extra stuff. Also, Mastering Organic Chemistry. I use that a bit in the next 2 presentations, and that's a very good website. All right, so here is a potential energy diagram just showing the energy of different compounds, right? And it shows that benzene is lower in energy than just a conjugated cyclohexene, right? So this is the delocalization of benzene lowers it in energy, right? So let's talk about what makes something aromatic, because there are a lot more molecules besides benzene that are classified as aromatic. There's 4 major criteria. You need the molecule to be cyclic. So if it's not a ring, there's no way it's going to be aromatic. You could have a conjugated system on a long chain, but if it's linear, it's not aromatic. So you need a ring of atoms. You need the molecule to be planar, meaning that all of them are in the same plane so that they can line up and do that delocalization. The molecule has to be fully conjugated, meaning alternating single double bonds. That's so that there's a p orbital at every atom in the ring so that you can have that delocalization. And then you need a specific number of p electrons or pi electrons. You need 4n plus 2 electrons, where n is 0 or any positive integer. So benzene is aromatic because it is a ring. It is conjugated, single double. It is planar, and it's got 4n plus 2 electrons. So 4n plus 2 pi electrons, right? So every double bond has 2 pi electrons, so that's 2, 4, 6. So you think of it as 4n plus 2 equals 6, and n would be the whole integer of 1 in that case. All right, so I've kind of outlined that here. 2, 4, 6, it's got 6 pi electrons, and that fits the 4n plus 1 rule. Some ions can even be aromatic, right? So notice that this only has 2 double bonds. It's a 5-membered ring. It has 2 double bonds. And then we've got a carbanion here, a lone pair, negatively charged. This is actually aromatic because this lone pair occupies a p orbital. So you'll see we've got the p orbitals from the double bonds, and we've also got the p orbital that the carbanion exists in. So we still have a ring. We still have a conjugated system of double, single, double, single, and then lone pair, which will count to keep that conjugation, right? And this particular molecule also has 6 pi electrons, so 2, 4, 6. And 4n plus 2 equals 6. That fits the, they call it the Huckel rule, where 4n plus 2 equals 6, n equals a integer or 0, so a whole number or 0. Heterocyclic aromatic compounds. Heterocyclic means there's something else in the ring besides carbon. So here we have an oxygen. And oxygen and nitrogen, these things have lone pairs. And these lone pairs can exist in a p orbital. So a lot of heterocyclic compounds are also aromatic because if you look at this here, we've got 2 pi electrons from this double bond, 2 pi electrons from this double bond, and then one of these lone pairs is in a pi orbital. So this is in a pi orbital sticking up into the plane, the aromatic plane. The other lone pair is sticking out away from the molecule, and it's not part of the ring. So here we still have 2, 4, 6 pi electrons. They're in a conjugated system. They are a ring. They are planar. So these count as as aromatic molecules. You can also have charged aromatic compounds, and what those are is it's a ring, and it's either got extra electrons or less electrons, so it has a charge, and they can also show aromatic stabilization. So here are some examples of aromatic ions that are actually stabilized that way. Here's some more aromatic heterocycles. These are some pretty famous ones: pyridine, thiophene, and imidazole. Imidazole shows up a lot in biology if you're interested in biochemistry. Now, all of these will fit Huckel's rule of 4n plus 2. So here we've got 2, 4, 6, and it's tempting to count this extra lone pair as 8, which would make it not fit Huckel's rule, but it's actually pointing perpendicular away from the plane of the ring. So this doesn't count. It's not in a p orbital, but these 6 are in a p orbital. So that's aromatic. And then with thiophene, we've got 2, 4, 6. One of these lone pairs counts as in the plane, and the other one's poking away from the plane, and it's not part of the pi system. So that fits 6, which is aromatic. And then also imidazole, we've got 2, 4, 6, and then this hydrogen is pointing away from the ring, and this lone pair is pointing away from the ring. So that fits the rule of 6. That takes a little bit of getting used to, because it's very tempting to say, okay, pyridine has 8, 2, 4, 6, 8, which means it doesn't fit the rule. But that's not true, because if we look at this, we've got all of the p orbitals, and this lone pair shown in blue is actually poking at a right angle in an sp2 orbital away from the pi system. So that does not affect the aromaticity. The aromaticity is in the 6 pi electrons that are delocalized here. So, using criteria for aromaticity, determine if the following molecules are aromatic. I want you to pause and try this now. All right, now that you've tried that, let's check out the answers, right? Number 1 is aromatic because it has 2, 4, 6 pi electrons, and this one is out of the plane. 2 is not aromatic because it's not fully conjugated, so it would need a lone pair here to really make it conjugated. 2 doesn't work. 3 is not aromatic because 4n electrons doesn't fit Huckel's rule, which is 4n plus 2. N is not a whole number, n is 1/2. 4 is aromatic because of reasons we saw in the previous slide. It has 6 pi electrons, and the lone pair is sticking out away from the ring. 5 is also aromatic because this lone pair fits in the pi system. 6 is not aromatic. It's tempting to say that it is conjugated, but there's 8 pi electrons, which would put n at 1.5, which is not a whole number, right? So that means it's not aromatic. 7 is not aromatic because it is cyclic, it is conjugated, but it does not have the right number of pi electrons. 8 is aromatic because we count one of these lone pairs in the system, which makes it 2, 4, 6 pi electrons. 9 is not aromatic because it's not fully conjugated. And 10 is aromatic because we have 6 pi electrons, and then this lone pair is pointing away from the pi system, right? So that's how you determine if something is aromatic or not. And determining if it's aromatic tells you a lot about its electronic properties and its reactivity. Now, this is bizarre, but cool. Polycyclic aromatic hydrocarbons. These are multiple aromatic rings fused together. So there's some pretty interesting compounds. I just want you to know that these exist. You're not necessarily going to have to know reactions of these because it can get very complicated very quickly. And you'll notice all of these are common names. These are not the IUPAC system. So I won't force you to name these, but know that they exist and they've got some pretty unique qualities. Okay? Now let's visit the characteristic NMR absorptions of benzene. We've already learned this, which is nice. The cool part is once you get to this part in Organic Chemistry 2, a lot of things start to repeat themselves. Because every chapter, we're going to be revisiting the NMR, IR peaks of compounds that we're learning about. And then you're going to see that a lot of the reactions start to overlap as well. So let's just remind ourselves that NMR absorptions show up in the aromatic region between 7 and 9 ppm for proton NMR, right? And then if you've got any hydrogens that are outside of the pi environment, you're going to see them showing up at about 2.5. So everything in this region is going to show up from 7 to 9 ppm. If you've got a hydrogen that is one carbon outside of the ring, it's going to show up at about 2.5. And then once you get at least 2 carbons away, they're just going to show up like saturated carbons at 1 ppm. To revisit IR absorption bands for benzene, right, you can see a CH stretch from 31 to 3000. You can see weak overtones from 2000 to 1665. You'll see the in-ring carbon-carbon stretch around 1600. And then you'll also see another CC stretch at 1500 to 1400. And then in the fingerprint region, you could also get some information that could be kind of hard to get. And here's just an example of an IR, right, where you can see your CH aromatic stretches, your alkyl stretches, CH aromatics, and then we've got CC stretches in the aromatic ring. And on the previous slide, when we said OOP bending, that's out of plane bending. That could show up in the fingerprint region. So depending on how messy your spectrum is, you could or you could not see it, right? So fortunately, this chapter was a little short, and here are 2 other excellent rings that I would like to suggest. Tolkien's Lord of the Rings and Wagner's Der Ring des Nibelungen, the Ring of the Nibelung. If you love really, really, really long excursions into fantasy, both of these are right up your alley. This is a 3-part book that probably goes well over 1,000 pages. And then this is a 16-hour German opera that has 4 parts to it. They both pull from the same Nordic myths, so it's kind of cool to see some of the same themes pop up. And they both involve rings. So, yep, that's just my moment to dork out. So enjoy. And next time, we're going to look at reactions of aromatic rings. So we'll get into how they react, mechanisms for that, and different reagents that occur. See you then.